Next, isothermal reversible compression. Isothermal reversible compression. For compression to take place, the pressure of the surroundings must be more than the pressure of surroundings. For compression, P external must be more than P internal. Therefore, P external is equal to P internal plus dP. Here dP is the pressure difference between the surroundings and the system. When the pressure difference between system and surroundings is negligibly small, therefore the degree of expansion or compression that takes place is also very less. That lesser degree of expansion takes place in each step is described as the reversible expansion or reversible compression. Here Tp tends to 0. dP tends to 0, P external. Therefore, since dP tends to 0, P external is almost equal to P internal. P internal means in place of P internal, we have PV is equal to nRT. P is equal to nRT by V. Therefore, here in place of P internal, we can substitute nRT by V. Therefore, work involved is minus P dV, that is equal to minus nRT by V dV. Next, in order to calculate the degree of compression taking place from V2 to V1, the above expression has to be integrated. To calculate the compression work done by surroundings. To calculate the compression work done by the surroundings from V2 to V1, the above expression has to be integrated from V2 to V1. Therefore, work involved is minus nRT. This is dV. Now the gas is undergoing compression. That means initially gas has been expanded from V1 to V2. During compression, the gas is coming back from V2 to V1. Therefore, here the final volume is V1 and initial volume is V2. Therefore, minus nRT ln V1 by V2. Next, since here V1 is less and V2 is more, therefore this total term is negative. Negative into negative, positive. Therefore, final expression will become positive. Here, since V1 is greater than V2, therefore the expression become positive. Whenever if we calculate the work involved, if we get the positive, then we can decide the type of the terminology that we can use. That is, now we can say the work done by the surroundings on gas is minus nRT ln V1 by V2 or nRT ln V2 by V1. Next, total work involved during expansion and compression. total work involved during expansion and compression. Therefore, W total is equal to expansion plus compression. During expansion, we have this expression minus nRT ln V2 by V1. Minus nRT ln V2 by V1. Next, during the compression, we got this expression minus nRT ln V1 by V2. Next, minus nRT ln V2 by V1. V2 by V1. Next, this is minus nRT ln V2 by V1. You represent, you bring V2 to the numerator. Therefore, it becomes, this is it becomes positive. So, minus nRT ln, so this becomes positive, V2 by V1 becomes positive. See, in both these expressions, N is the same, R is the same, T is same. This is ln V2 by V1, this is ln V2 by V1. Here, during this expansion, gas has undergone expansion from V1 to V2. During compression, the gas is coming back to the same original position, that is from V2 to V1. Therefore, the magnitude of the V1 and V2 in both the expressions are same. But one is negative term, the another one is positive term. Hence, the sum will always become 0. Therefore, the net work involved during the expansion and compression is 0. Next, whenever if the net work involved during expansion and compression is 0, then that process is considered as a perfect cyclic process. Therefore, the isothermal reversible expansion and isothermal reversible compression is together described as the cyclic process. In this cyclic process, the system has came back to perfectly identical position. Therefore, in general, cyclic process means the process after so many stages, if the system comes back to original position, that is called cyclic process. In order to know whether the system came back to original position or not, you just observe the sum of all the mathematical terms. If the sum of all mathematical terms becomes 0, then that process is described as the perfect cyclic process. Next, the thermodynamic changes involved in the isothermal reversible process. So, say therefore, according to first law of thermodynamics, the first law of thermodynamics we can represent like this: dou Q is equal to du plus PdV. This is first law of thermodynamics. Now, we are studying the thermodynamic changes involved in the isothermal reversible process according to the first law of thermodynamics. Here in the isothermal reversible process, we are maintaining temperature as constant. When temperature is constant, internal energy change is 0. Therefore, at constant temperature, du, internal energy will remain constant. Therefore, change in internal energy is 0. Next, when the change in internal energy is 0, therefore, dou Q will become equal to PdV. That means this is the amount of the heat change involved in the process, which is equal to quantity of the work involved in the same process. That means in isothermal reversible process, because of the constant internal energy, therefore, the heat absorbed or heat exchanged with the surroundings finally become equal to the work involved in the process. That means dou Q is equal to PdV. Next, so according to the same first law of thermodynamics, when the internal energy is 0, the enthalpy change also becomes 0, because we have the expression, we have del H is equal to du plus PdV. This is a, so this enthalpy change, it can be represented like this also, differential of PV. This is the enthalpy change. The enthalpy change is equal to du plus differential of the PV. At constant temperature, the differential of PV is 0, because at constant temperature, differential of PV is equal to 0. Next, du is already 0, therefore enthalpy also becomes 0. At constant du is 0, du is also 0, therefore enthalpy change is also 0. That means at constant temperature, internal energy change is 0, enthalpy change is 0. Therefore, dou Q is equal to P dV. Next, thermodynamic changes involved in isothermal irreversible irreversible process. See here, temperature is a constant, therefore del du is 0. At constant temperature, internal energy of the system will remain same. Next, enthalpy change is also same. Therefore, according to first law of thermodynamics, this is the first law of thermodynamics. This is 0. Therefore, dou Q is equal to P dV. That means in the isothermal irreversible process also dou Q is equal to P dV. That means heat exchanged with the surroundings is equal to work involved in the process.